All right. Well, we are ready to get started, maybe with some questions over 6.3. Oh, well, actually, I lied. 6.4, right? 6.4. Let me turn the page here. Okay. So any 6.4 questions? Yes. 27. Let's take a look. We've got a technology one. Okay, so 27. We've got y equals 2x to the negative equals 2x to the negative 3/2. And y equals 2. We've got y equals 16. And x equals 0. And we're revolving around the x-axis. Okay, so let's take a look at what we got here. So let's do the easy stuff first. Y equals 2 is easy enough. We've got like y equals 2. Y equals 16. Somewhere up here. X equals 0 is the y-axis. So that's here. Okay, so we've got a boundary, a boundary, a boundary. And then what's the other one look like? So what does y equal 2x to the negative 3/2 look like? I don't have my calculator on me right now, but what should it look like? So that's 2 over x to the 3 over 2, correct? So that's bigger than x, right? So if it's bigger than x, it's going to maybe get close. Let's see, what's the best way to do it? So it's going to maybe do something of this nature. So when x is very, very small, then the 2, let me think about that for a second. Yeah, so if x is super tiny, then this is going to be super big, right? And if x is super big, then this is going to be super tiny. Agreed? Okay, I think that works. So it's something of this nature. And then, so there is a little bit of overlap right there. And then we've got this. And so this, it's going to be shaped something like that. And now they say, go ahead and take that and revolve it around the x-axis. So we're going around the x-axis. Okay. When we spin it, what will it look like? Well, it's kind of a big circle. It goes in a little bit, in a little bit. I have that edge. It kind of goes that, and that. And except has a little hole in the middle, right? So in the middle, we've got this. Hole through the middle. Okay, so we've got an idea what this thing looks like. We'd like to know what the volume is. So this is certainly a good problem for shells, because if we cut this direction and spin, then we get a shell, right? Now, just like I've asked you before, if I start making cuts this direction, this kind of cut, what axis is getting cut? Y-axis, which means all the stuff inside the integral is y. So whatever gets cut, that's what goes inside of the integral. If I could say that like 100 times in a row, I would, but it's annoying. But it's kind of like, it's amazing to me how often on exams I've said that like 10 trillion times, and then somebody writes this integral using x's. And it's like, no, you can't do it. Okay, it's got to be y. And the way that you can always know is, what kind of a cut are you making? I'm making a horizontal cut. What axis gets cut? The y-axis. So what goes in the integral? Y stuff. If you get just that alone out of this time today, that's like gold. Okay, and it doesn't matter if you're doing shells or washers or discs, it's always the same. Okay. By the way, could you theoretically do this using discs or washers? Yeah, it's going to be really, really hard, but you could do it. But then you would be cutting this direction, meaning that the x-axis would be getting cut, which means that your integral would need to be in terms of x's. Make sense? But definitely this is the easier way. Okay, so our volume that we're looking for here should be the integral from something to something. So this is where I start cutting at 2. This is where I stop cutting at 16. So we're going to take an integral from 2 to 16. And then the equation that goes inside this integral is what? 2 pi r. Exactly right, 2 pi RH. And that's actually just the outside area of a cylinder, is 2 pi RH. Because if you think about it, right, you cut the cylinder open, if you watch the lecture, it's just like the circumference is 2 pi r, and the height of the cylinder is h. So it's just 2 pi RH. Okay, so what goes inside is 2 pi r. Okay, so what's the radius of one of these shells? If I'm sitting up here at a point y, then what's the radius of the shell? In this case, just y. That distance is y. In other words, if I was at 2, what would be the distance around? The radius would be 2. If I'm up at 16, the radius would be 16. If I'm at y, the radius would be y. So I put in y. And then I need the height. And the height in this case at y is the top function minus the bottom function. So the top function is this guy. But remember, I need to put in y stuff. And then the bottom one is just what? X equals 0. So I need to just solve this thing for x. Okay, so if I wrote y equals 2 over x to the 3/2, right? Then I could move the x to the 3/2 up here. In some sense, like I could cross multiply. So I get y x to the 3 over 2 equals 2, divide both sides by y. I get x to the 3 over 2 is equal to what? 2 over y. And then I guess I'd have to raise both sides to like the 2/3 power, right? And so I'd get x is equal to 2 to the 2/3 divided by y to the 2/3. And so that's what I want to put in. So this is the top function is 2 to the 2/3 over y to the 2/3 dy. Now, I could simplify this a little bit, well, quite a bit. I've got a 2 that's a constant. I've got a 2 to the 2/3 that's a constant. What's 2 times 2 to the 2/3? How many thirds is this 2 raised to? So this is 2 to the 1, right? 1 is otherwise known as how many thirds? 3/3. right? So this is 2 to the 3/3. This is 2 to the 2/3. If I add those together, I get 2 to the how many thirds? Yeah, 5/3. Thank you. So 2 to the 5/3 times pi times the integral from 2 to 16 of, okay, I took the pi out, I took the 2's out. I just have y divided by y to the 2/3, which is otherwise known as y to the 1/3 dy. Everybody like it? Any questions? I see some people just staring at it, so I'm going to wait 1 second to see if there really are any questions. Looks like somebody chatted, so let me look. Interesting.
How do you know to do a
Oh yeah. The reason why is I wanted to combine the 2 and the 2 to the 2/3. So really what that, I'll go to the side for a second. If I have 2 times 2 to the 2/3, right? What I really have is this is 2 to the 1st times 2 to the 2/3, correct? And what I do with exponents when it's the same base is I add them, right? So this is 2 to the 1 plus 2/3, right? And so this isn't so nice. So if I got a common denominator for the 1, it would be nice. So that's 2 to the 3/3 plus 2/3. And now it is nice. And so that's just 2 to the 5/3. Make sense? Cool. Any other questions? Yes, sir. Yes. So similar, actually, in some ways. I've got y to the 1st, right? So y to the 1st is otherwise known as y to the 3/3. And so if I have this on top, y to the 3/3 is on top and y to the 2/3 is on bottom. When I divide like that, I subtract the bottom one from the top one. So this is equal to y to the 3/3 minus 2/3. And that's my y to the 1/3. Sound good? Okay, I think we're ready to keep going here. Let me erase a little bit. So far, we haven't needed our calculator per se. And I think,
why is the radius y?
Yeah, so the radius is just y because if you look at, okay, let's say that I'm at the point y. Then I say, if I'm at the point y, and y can vary between 2 and 16, right? It's going to take all of those values, so to speak. And so I'm saying at y, where it's going to take a value between 2 and 16. So for any y in there, what's the radius? And so if I'm just sitting at random y point, then how far am I from the middle? And in this case, it's just y. Typically, it will just be like x or y if you're revolving around an axis. If you're revolving around something weird like y equals 3, then you got to be more careful. Does that make sense?
Yeah.
Because that means that the radius is actually, like, let's say I was revolving around this line. Now the radius could be y plus a bunch more. But since it's just the axis, it's pretty easy. It's just y. Does that make sense?
Yeah.
Okay. Any other questions before I move on? Yes.
I'd like some logistical questions. You said there would be help sessions in Lemons.
Yes.
What time does that happen?
I believe it's 7 to 10 Sunday through Thursday in Lemons 15.
Sunday through Thursday?
Sunday through Thursday, yeah. I believe that that's right. That's when it's always been. So.
And then also, you're really good at like visualizing these graphs. We're not going to be using it for every test. How do you
Yeah, so there's a lot of different ways to think it through. First of all, on a test, I'm not going to try to like trap you and say, I'm going to throw the hardest function at you you've ever seen and you better know how to graph it. You know what I mean? That said, sometimes like even the stuff that I do throw at you, you're kind of like, oops, I forgot what y equals x squared looks like, right? But in Cal 1, what did we learn all about? How to figure out what a function looks like, right? So theoretically, just using your knowledge of calculus, you should pretty much be able to figure out. And if all else fails, like you don't remember the function, calculus isn't helping you figure it out, you could just like do a t-chart and plug in some points. That's like not optimal, but it works. You know what I mean? Yeah. Okay, so let's keep going. So we've got this fun thing over here, but this we need to take the antiderivative of. So we'll just leave the 2 to the 5/3 out here. We have the pi out here. Then we take an antiderivative of y to the 1/3. Raise the power by 1. 1/3 plus 1 is otherwise known as y to the 4/3. And then I divide by 4/3. Dividing by 4/3 is the same as multiplying by what? 3/4. So really, I just want to multiply this by 3/4 and evaluate from 2 to 16. All right. So I still have this rather terrible number outside. 2 to the 5/3 pi, and then I plug things in. So 16 to the 4/3. Fun. So is there any nice way to do that? So 16, there's no nice cube root of 16, unfortunately, right? So that's not so nice. Okay, bummer. Let's go ahead and just write it out then. So by the way, if you wanted to, you could pull this 3/4 out with the rest of this stuff. Maybe it would make our life easier. So I'll just say this, I'll pull the 3/4 out and then just plug into the y to the 4/3. So you got 16 to the 4/3 minus 2 to the 4/3. And that's equal to something, right? That's where they probably want you to use your calculator and just figure out what is that mess of stuff. But we're all done, basically. We just have to evaluate it. Sound good? Yes, sir.
So how much of the homework would you say we should do calculator?
Well, really, the only ones you really should need to are the ones that have the little blue T next to the problem. This one did. It had the little T, and that's kind of like a warning sign that, like, without your calculator, this might be a little hard. Although, if I was going to be like super lazy, which I don't recommend, I would just like say, "Oh, look, there it is," and it's like, it's not like the prettiest thing I've ever written, but it is right. You know what I mean? So I don't need the calculator unless I want to do a little bit better than this. Yeah. That's a really good question. Here's my best answer to that is like, use common sense. Like sometimes people ask me that question and then they get mad at me later when I mark something off. So here's a great example of something you should simplify. This is your answer at the end of the problem. Okay, if somebody writes this at the end of the problem, I'm going to take off a point every time because that's just like makes me want to cry. You know what I mean? While I'm grading. But on the other hand, if there was something like if you box that in, I'm not going to be like, no, that's x squared minus x. Because it's kind of like, it's equivalent. You know what I mean? So if it's kind of like, you're not really making it any better to simplify, then I'm okay. Another one that would be sort of bad would be like if you had x cubed minus x squared divided by x, and you box that. That's not so great because that's clearly x squared minus x. right? So it's kind of like if there's an obvious simplification, then I would expect that you would have made it. If it's not so obvious if I need to move this in or not, then I'm going to accept both of them. And I'll probably err a little bit more on the side of giving you the credit if you did everything right and you got a right answer. But if it's just like, wow, that's really not very nice. Or like if somebody said that the answer is 3 squared, it's like, which is 9, right? So if something's obvious, do it. If it's not obvious whether or not you need to simplify, then leave it, and it should be fine. Other questions? Hello, Briggs. What people are thinking.
Elsie?
What's that?
No.
Oh, yeah. Okay, 1 second here. Yes, somebody asked, so somebody online asked, can you explain when you know to use like the disc or washer method and when you know to use the shell method? That's a really good question. So let me give just like an example. And there's an easy answer, and that is do whatever you want to. Typically both will work, provided you can actually do the integral. Okay, so what you want to do is just like make life as easy for yourself as possible. So let's say that I had like, I'm not going to put in any specific, let's say that I had something like this was my region. Okay, here's my region. I don't need this is just f of x. And let's say that I want to spin that around the x-axis. Well, I have choices at this point, because if I want to spin this guy around the x-axis, then what comes out is something like kind of the tornado on its side, right? So that's what comes out. And so I could either chop it this direction, which would give me all discs, or I could chop it this direction, spin it, and get shells, right? So if I go one direction, it's discs or washers. If I go the other direction, it's a shells problem. So what you have to do is you have to make a choice. You have to say, do I want it to be a washer's problem or do I want it to be a shells problem? And the way you make that choice isn't because you like one better than the other. The reason you make that is because you say, which cut do I really want to make? So maybe there, you really want to deal with this as a function of x for some reason, not a function of y. Like maybe it would be really, really hard to solve for x, but it's already set up as a function of x, so you'd rather just use x stuff. Does that make sense? If you know that, then you want to make a cut of the x-axis, right? So you have to choose, am I going to cut like this or am I going to cut like this? And if you say, I really want to make this cut, well, if you make that cut and you spin that cut, then you get a disc, right? And so you say, oh, since I want to make this cut, when I spin that cut, it cuts the x-axis, I get a disc, so I want to use x stuff in a disc method. Does that make sense? So that would tell me what I want to do. Now, maybe I say, no, I don't want to do that. I want to cut this way. Then when I spin it around the x-axis, I get a shell. and then I know I'm cutting the Y. I need Y stuff in a shell method. So it depends on what you want to do. And really, if I saw one of these problems, the question I would ask is, what kind of a cut do I want to make this pretty easy on myself? So do I want X stuff or do I want Y stuff? And if you can make that decision really easily, like, oh, it's all set up for X already, then why would I want to convert everything over to Y? Then make the cut that makes X, and then figure out based on which axis you're revolving around, whether or not it's a shell method or a disk method. Hopefully that's helpful. If you get that piece, that's like a huge part of like the first exam, is like, can you just do what I just talked about? Can you make the decision? Is it a shell method, a disk method, or a washer method? And should the X's or the Y's go inside? If you've got that, you're well on your way to doing very, very well on the first exam. Okay, I think somebody asked an actual problem on here. They said 6.4, number 10. So let's look at it. Okay, so we've got that Y equals 1 plus x squared to the negative 1, 1 plus x squared to the minus 1. We've got y equals 0. We've got x equals 0. And we've got x equals 2. And the axis we're revolving around is the y-axis. Okay, let's pretend for a second that we didn't know that this was the section about shells. Okay, so if we didn't really know what method to use right now, then how would we kind of figure this out? They're very nice and they gave us a picture, right, of what this thing looks like. It sort of comes down like this, and then it like cuts off at 2. Right, so it kind of has this shape. And then it says, please spin that guy around the y-axis. And so now I can, if I want to kind of draw a picture, kind of looks like a bell. Right, kind of got that bell shape going on. And now my question is, well, which way do I want to cut it? Now, in one way, if I cut this direction, is there always one thing on top and one thing on the bottom? If I cut it this way. So like if I draw a line anywhere through this object, is there always a function on the top and a function on the bottom? That's good. Now, I could cut this way, but what happens? When I get to this point, if I cut this way, this guy's on top, this guy's on bottom. When I get to here, this guy's on top, this guy's on bottom, which is a different function. That's annoying, right? It's annoying to have to switch. And so I say, no, 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 no. I don't want to switch. Is everybody with me? It's like, I just want to do one integral, not two. So the way that I can get out of the problem is just make sure I cut it this way. Does that make sense? So I decided this way is best. Now if I spin that shape around the y-axis, it would look like this. And I say, wait a second, that looks a lot like a cylindrical shell. And that's the method we need to use. So I decide what the cut should look like, spin that cut. When you spin the cut, it tells you the method. And what should go inside the integral, x or y stuff? It's one of those, x or y. Which one? Yeah, I'm making cuts this way. What axis is getting chopped? X. So all the stuff inside, so I'm going to integrate from an x to an x with x stuff dx. Make sense? Okay, let's do it. So my volume is equal to integral. I start cutting at an x, and I stop cutting at an x. So where do I start? 0, I end 2. So 0 to 2. Now I say, what was the method? I said it was a shell. So shell tells me I need to put in 2 pi RH. So 2 pi, it's easy. R, okay. So the R is, if I'm just sitting over here at a random x, how far am I from the center of that shell? Yeah, in this case, I'm just circling around an axis. So typically that means it's just x or it's just y. In this case, it's just x. And then I need to put in what is the height of that shell at x. So how far is it up? Well, it's the top function minus the bottom function, but the bottom function is just 0. So it's just the top function. And the top function is, it needs to be in terms of x, but fortunately this one already is. So I just need to put that in. By the way, 1 plus x squared to the minus 1 is otherwise known as 1 over 1 plus x squared dx.
Can you explain the top function minus the bottom function?
Yes. So here, all that I really care about here is I'm at x, and I want to know how tall is this shell at x, right? Or how tall is this shell at x? Or how tall is this shell at x, right? So given any x, how high do I have to go? And the answer is, in this case, well, what's the difference between these two functions? This top function and this bottom function, whatever it is. So the top function in this case is here. The bottom function in this case is here. So what is this one? Well, that. And what is this one? Well, that. Right? So I take the top function minus the bottom function, which just happens to be 0 in this case. If this were some funky thing down here, then it would be much more complicated in terms of the rate, the height, right? But in this case, since the bottom is 0, it's pretty straightforward. And I just take the top function minus the bottom function for the height. Does that make sense?
Yes.
Yeah. Are we ready to do some integration here? Okay, so I can pull out my 2 pi, and I get 2 pi times the integral from 0 to 2 of, if I put the x up with the 1, I get x over 1 plus x squared dx. And now I need to take an antiderivative of that. Any ideas on how to go about such a thing? Yes, sir. Yep, U-substitution. And what do you think we should U-sub for? Yes. Very good. So U is 1 plus x squared, which means that du would be, what's the derivative of 1 plus x squared? Yeah, 2x dx, right? Well, I don't have a 2x up here. I have an x dx, but I don't have a 2x dx, but I'm very fortunate, right? That I just happen to have a 2 sitting out here. I could just pull him in, and then I'm good to go, right? So what I'll do is I'll just quickly move the 2 into here, and now I have everything I need to make my U-substitution. So once I do, I say pi times the integral 0 to 2 of 2x dx is otherwise known as du. And on bottom, 1 plus x squared is otherwise known as u. Correct? Now I can take an antiderivative. So this is pi. What's the antiderivative of 1 over u? ln of u, very close. Absolute value of u. It's ln of absolute value of u. Yeah. So this is ln of the absolute value of u evaluated from 0 to 2. And now we can just plug things in. So we still have the pi sitting there. Then I want to plug in 2. Obviously, the absolute value. If you would have used u and not absolute value of u, everything would have been fine this time because it's the absolute value of all positive things, right? But if not, that would have been more challenging. Okay. Oh, and I did something horrible. Good, I'm glad I caught it now. These are wrong, right? That was very horrible. So I didn't change my limits of integration. Yes.
If you just plug that in,
You could. So what you could do is at this point, you could change the u to 1 plus x squared and then plug in the 0 to 2. But if you want to leave it as u for the plug-in, then you need to change it. Now, when I took calculus 1 and 2, and I learned this, for whatever reason in my mind, it was easier for me to plug back in the x's and then to evaluate an x. So I knew that I didn't mess up on my limits of integration, and that's how I like to do it. Now I kind of, after teaching it a lot and doing lots of different things, I'm like, yeah, that's horrible. It's just like messy to plug back in and stuff. It's so much easier to just move to u and never look back. So that's what I recommend ultimately. But I even was a culprit of doing it the other way. So I forgot to plug in. So if I plug in 0 for x, u would be what? 1. And if I plugged in 2 for x, u would be 5. Yeah, so that's what I should have done. So this is from 1 to 5. And then we plug in, and I get pi. Oh, what am I saying? I already wrote pi. Pi times ln of 5, or absolute value of 5, which is 5, minus ln of 1. And what's ln of 1? Close. 0. Yeah, 0. So this is just ln of 5 times pi. And we're done. Does anybody know how I figured out that I messed up? Because my limits of integration were from what? 0 to 2 right here. And what's ln of 0? It's undefined. ln of 0 isn't a thing. And so I was kind of like, I don't know about that. And so I was able to say, oh yeah, messed it up. So yeah, ln of 0 does not exist. So that wasn't good. Okay, so we got it. Any questions? Did I answer your question, whoever asked the question, hopefully? Yes.
Is there somewhere we should go to like stuff that we should like break down into these math classes we got this, like it's like you have the institute one plus no, you have
Yes.
That's
Yeah.
so is there other things that we just have to know?
Yes. So I would say that just like every common derivative or antiderivative from calculus 1, I would expect you to know. So like, derivatives of trig functions, exponential functions, logarithmic functions, those are the big ones. And inverse trig functions also, right? Derivatives of inverse trig functions, antiderivatives of inverse, or things whose antiderivatives are inverse trig functions. All of those, for sure, are really important, and we'll use all the time. Other questions? Yes, sir. 18. Okay. And it is like 20 degrees hotter in here today than it has been any other day. I'm just like, I'm about to start sweating pretty hard. It's not that fun. Okay, number 18. We have y equals 6 minus x. We have y equals 0. X equals 2. And x equals 4 about the y-axis. Okay. So let's take a look here. We've got y equals 6 minus x. So 6 minus x looks like 1, 2, 6. 6 minus x, intercept is 6. Negative x makes the slope minus 1. Here we go. Then we have y equals 0, which is my x-axis. We have x equals 2, which is here. And we have x equals 4, which is here. And then we want to spin that around the y-axis. And again, so here's my region. And when I spin that around the y-axis, I'll get something that looks sort of like, has kind of a hole in the top, comes down a little bit, down a little bit, something like that. Okay, and it's hollow. All right. What's the volume? First thing we should decide is this a washer method problem or is this a shell method problem? And the answer is it's both, right? But there's one that's really nice and there's one that's really ugly. And the question is, how do I want to make cuts? I can cut this direction or I can cut this direction. Why is it that cutting this direction makes me feel bad about myself? Yeah, what's that? Yeah, I'm going to have to break it into two intervals, right? Because here, up here, this is the top function and this is the bottom function. Down here, this is the top function and this is the bottom function. So it switches. I don't like that. I don't want to switch somewhere from one function being the top to another function being the top. It would be really nice if it was just one function where the top the whole time and another function where the bottom the whole time. But if I cut this direction, then it's always the same, right? This is always the top function. This is always the bottom function. That I like. So if I'm taking a cut like this and spinning it, I get a shell, which isn't shocking since this is the section on shells, right? So that's what I want to do. And now I know which axis is getting cut when I make my cuts. And I know what method is being used because when I spun that cut, I got a shape and that shape was a shell. So I'm using the shell method and what axis got cut in this case? X-axis. So all the stuff I'm integrating from an X value to an X value of X stuff dx. Make sense? And what goes inside, since I spun it and got a shell, I'm using the shell method. Sound good? Let's do it. So volume is equal to integral from, I start cutting at what X value and I stop cutting at what X value. Yeah, this is 2, this is 4, so I'm integrating from 2 to 4 of 2 pi r. Okay, so if I'm at some X value right here, how far am I from the center of the shell. Just x, right? The center of the shell is the y-axis. So how far out is this from, is x from that y-axis? Well, x. So x goes here. And then I have the height. But the height in this case is the top function, which is this line, minus the bottom function, which is this line. So, and I want it in terms of x. So it's 6 minus x minus 0. In other words, just 6 minus x dx. Yes, sir.
Learning the first x for the r.
Yep.
Would you not do x plus 2?
No. You would if the radius were back 2 more. Because x is that, how far is it from 0 to the point x? X. That's right. And that's basically what I'm asking is, how far is it from the thing you're rotating around to the point you're concerned with? Now, if you were doing something different, like let's say you had this same shape, right? That's our little shape that we're spinning. But now I say I want to come back to -1 and spin around -1. Right? So now what I would do, and this is important, is if I were at a point x, then I'd say, well, how far is x away from -1? Well, it's x to get back to 0 plus 1 more. So the radius, instead of being x, which is this distance, it would be x plus 1, which is this distance. Does that make sense? And that's what you just have to look for, is like, how far is it from my x to the center of that cylinder? And whatever that is what you put in there for the radius. Sound good? All right, let's keep going here. I can pull out the 2 pi, 2 pi, 2 to 4, and then inside, if I distribute, I get 6x minus x squared dx. It's a fairly easy antiderivative. So I get 2 pi times antiderivative of 6x is, I suppose, 3x squared. And antiderivative of negative x squared is negative x cubed over 3, evaluated from 2 to 4. So we'll plug it in. 2 pi hangs out. Plug in the 4, and I get 4 squared is 16 times 3, 48, minus, what's 4 cubed? 64, very good. So this is 64 over 3, minus, plugging in 2. 2 squared is 4 times 3 is 12. And then 2 cubed is 8, so minus 8 over 3. Now we just need to combine things. We'll just let the 2 pi hang out again. And then we get 48 minus 12, otherwise known as 36. And then we get minus 64 over 3, minus, so plus 8 over 3. So in other words, what's like negative 64 plus 8? Negative 56 over 3. Is 56 divided by 3 a whole number? No. Sad. So what's 36 times 3? Yeah, 108. So this is the same as 108 thirds, right? 108 minus 56 is what? 52. So this is 2 pi times 52 thirds, right? I guess I could multiply that by 2, and I get 104 pi over 3. And unfortunately, 104 also is not divisible by 3. So it's about as good as it gets. Any questions? Okay, So last word before you go for today is if you learn nothing else, this little trick of which way to cut and when to know, how do you know to use which method? It's all about your first slice. So you get to choose the slice, which is the most advantageous to you, and then just spin that slice and see what shape comes out. If it's a disc, use the disc method. If it's a washer, use the washer method. If it's a shell, use the shell method. So you choose the slice and then see what happens, and it will tell you what to do from there. Does that make sense? Question?
Yeah, I was gonna ask, is that how it's going to be in the test?
Yes. I'll just give you a situation. Just like this, I'll say, okay, take the region bounded by these curves, spin it around the y-axis, and what's the volume? And so you will get to choose which way to go. And so ultimately, there's two different ways to answer the question, because it's not wrong to do two integrals and do in this case, it would be the washer method. It just creates two integrals. By the way, a lot of times on these exams, I'll just ask you to set up the integral. As soon as on a lot of these problems, this would be the answer. Because ultimately, integrating should be fairly easy if you know your Calculus 1. There may be a question or two where I actually have you integrate, but for the most part on the first exam, I'll just have you set it up so that I know if you got here, you're pretty much good to go to get the answer. Did you have a question too? Oh, that was it. Okay. Yes, sir.
Will we have to know the area of various shapes by heart?
It would be good, especially the simple ones. The area of a circle, the area of a square, the area of a triangle. Those are the kinds of things that I would kind of expect. If it's the area of an octagon, I think I'll assume you don't know that. You know what I mean? So if it's just your basic shapes, yes. If it's a three-dimensional object, typically I will assume that you don't know those formulas for the volume of a sphere. Maybe you do, but if you don't feel bad. But if it's a basic two-dimensional shape from geometry, then I would expect that you do know that. Yeah. All right, that's it for today. Have a wonderful day, and I will see you on Friday. Some of you.